So the MOD Alliance, that stands for the Marco Polo, the Obama Next, and the Diversities Project, is a collaboration between these three projects that were funded in the same call. And as part of the efforts to synergize and maximize the impacts of the project, we have established this MOD Alliance, and the webinar series is one of the joint activities that we have been developing over the past more than 1 year. Yeah. So today it's the sixth webinar, and there will be already a seventh webinar, and I think that Marco Polo and Obama Next will finish later this year. Diversity still have a few more months, but please follow our websites and our social media so that you are aware of the future topics and webinars. So today I'm very happy to announce that we have two fantastic speakers. They are part of the Obama Next project. One is Josean Fernandes-Salvador from AZTI from Spain. He's a data scientist from computing and artificial intelligence studies, with different skills and the expertise needed to translate data into valuable information for marine research, policy, and industrial applications. He has many years of working expertise in this area, over 15 years in Spain, Finland, and UK, and in the last couple of years, more than a couple of years, in AZTI, he has been working on enhancing its big data and artificial intelligence research, combining large and heterogeneous data sets with state-of-the-art machine learning and decision support systems, mainly to aid the industry and policy to adapt and mitigate climate change. And the second speaker will be Mihailo, and he's from the University of Aarhus in Denmark. He's a postdoctoral researcher focusing on computer vision and machine learning research in the marine domain, with applications to upscale monitoring of marine ecology. He obtained his PhD in marine computer vision from University of Auckland in New Zealand, and he was formerly a professional software engineer and consultant on computer vision and machine learning for the Auckland regional government industry. So without further ado, I welcome both speakers. Josean will start and will be followed by Mihailo, and then we will leave the Q&A session for after his talks. Feel free to write in the chat the questions that you have, and we will read them and discuss them afterwards. So again, thank you very much for being here, for listening and participating in this webinar. And Josean, the floor is yours.
Thank you so much, Miguel, for the introduction. I just realized that even I am a computer engineer, I have been working on marine research and fisheries already for 19 years. I was making the numbers now. And it's something I have enjoyed, this thing of putting together multiple disciplines. I think successful research needs this multidisciplinarity and teams of people with different expertises. And I actually did my PhD applying machine learning to fisheries research and with fish recruitment prediction and with zooplankton automatic classification, like more than 15 years ago. And there is some common things I have found during my experience about what is needed that we can trust any system with artificial intelligence, which actually applies to any data analysis. I mean, even we are speaking about artificial intelligence here. Actually, people that has been working on data analysis, they will think, well, this is not only for artificial intelligence, but artificial intelligence can be very powerful, but also have some issues of the lack of sometimes of understanding. So this thing of how we can trust artificial intelligence is something that has been around for long time, even maybe with recent advances in machine learning is more visible. And in this work we did, for example, for the European Parliament, is already in 2022, they was looking at trying to put some legislation where they want to potentiate the use of artificial intelligence because the advantages it can have, but they also want to make sure that it's making a way that is ethical, that can be trusted, that don't go against people. And I highlight this work because one of the things we already identified there as computer scientists is that one of the main barriers that are at our hand, something we can deal with, is the biased training sets and data. I mean, the data we have sometimes have errors or are only part of the reality. And identifying that and dealing with that is an important part of making systems that can be trusted. Actually, in a recent publication, actually from Obama Next, in collaboration with other projects and also in collaboration with the ICE's machine learning group, we identify all those things that are needed for developing systems or testing or evaluating systems to see if they can be trusted. There's a part of socioeconomic, a part of data governance, but today with the time I have, I want to focus on the technical part that is related with what I say about biases dataset. Here there's some references about, if you want to read more about what I'm going to speak about, how we can ensure that or reduce the chances of having biased data, or that we are able to identify these biased data, or whether our algorithm can perform well or not. One part is the robust statistical validation, and there is and statistical validation is based on that we divide our data in training and testing, but there is many ways of doing that. Some are very old and they are known in machine learning and computer science literature. They are not very good because they have their own issues and biases. And there is one or two techniques that seems to be some agreement that are the best way of partition your data in training and testing. One is repeated cross-validation, another is bootstrapping. Cross-validation is based that you divide your data in many folds. Like in this case, we have 4 folds, and you use one for testing and the rest for learning the model, and then you repeat this as many times as fold you have. So you can train with this and test with this 4 partition, train with 1, 2, and 4 and test with 3, and so on. And that not only gives you different estimates of the error, that allows you also to see what is the variance of that error. And you can go further and repeat this many times, because maybe depending on how lucky you was with the initial partition of data, you might get some results. But if you randomize the data, do the partitions again, you might get another result. And if your data is not biased and if your data is well represented, it's less likely that there is differences between different ranks. But if there are differences, you can start analyzing where they come from. One common use is to do 10 times 5-4, for example. Another technique is bootstrapping. Bootstrapping is based on doing many runs. Some literature uses to say at least 1,000. Some people will say at 100 maybe it stabilizes. But the difference with the previous one is that you don't divide the data in different folds. What you do is you pick randomly data, and you can pick the same data more than once. That means that there is a small chance of overfitting, but this approach, what it's trying to do is do many runs until you approach something that is stable, and look not at both the power of fitting, whether your model fits well the data, but also the power of generalization. What cross-validation, you usually are looking more to look at the generalization power. And nowadays we have to be aware that many of the powerful tools we have tend to overfit data. So I will suggest, if you are doing things like deep learning, maybe use better cross-validation, but both has a good statistical properties that allows you to test your data and identify issues. I speak a little bit at the beginning about there's some ways of data partition that are not very good and still very well used. One is hole out, where people say, I will keep 80% of my data and test with 20%, but that is very dependent on how you partition the data. And in a work I did during my PhD thesis, I did an experiment. What if I, by chance, take the best partition, where I do a 80%, 20% split? I can get 100% accuracies. That was not realistic. If I do more robust validations, like for example, here I have cross-validation, what you can see is now I don't have 100%. I have another number that is lower, but I also can estimate the variance of my error. And you can see there is an issue here. The variance is very high. As I do repeated cross-validation, my numbers keep going down and my variance goes down. So you can see that this is more robust estimation of my error, because I know that probably I'm going to be predicting well around 70% of the times. Another thing that allows the repeated cross-validation and bootstrapping is because we do many runs of validation, we have many estimations, we can do statistical tests if we want to compare how well different models perform. For example, here, since we have this estimation of error where we have this 73% plus the variance, we can see already before doing the statistical test that probably these are not significant different, because even there is maybe 8% difference here. The variances are around 10%. So it's likely that the statistical test is going to say that they are not statistically different, and probably is, or with very low significance. So we can see how statistics can help us to make sure that our system will report good performance and we can identify some issues. Still, another issue we can find is that sometimes we don't have only a model. We have also a certain pre-processing of the data, like discretization, missing data imputation, selection of variables that can overfit the data in a way that when the model, even if you use a very simple model, the model overfit the data because the pre-processing was overfitting the data already. So this highlights that the importance is what you value. If you have a pipeline of methods, you should do the train test data split before any analysis is performed. So you can validate all your pipeline of methods and avoid that you overestimate the performance because you have been doing overfitting in the pre-processing. This is also something that can be seen with the now increment of use of deep learning. Deep learning can overfit data easily, and you can even overfit it more because it has something that is parameter training. So if you want to validate your deep learning methodology, you also have to look if you have to validate all the pipeline and make the train test split before you do your parameter optimization. And then once you know what is the good performance, what is the real performance of your model, then you can train your model with all the data and with your hyperparameters. But sometimes that is not enough because, I mean, sometimes the statistical performance can tell you that about looking at where there might be issues with your data, but sometimes the data you have is not a complete and full vision of what was there, because maybe the sampling method has limitations, or because there was a human error that some data was lost, or what. So we need what is called ground truth. Try to find other sources of information that you can compare with. Maybe that other sources of information have their own errors, and they are not really the truth, but looking at the discrepancies between different sources of information, your system and other sources, you can identify or issues in your data that you was using to train your models or your models, or that other data that your models can complement. I want to show here a couple of examples. Here we have been, for example, identifying tuna fish in vessels, in tuna vessels, where what was, apart from the statistical validation, what we did is we compared what was being recorded in the vessel with what was the experts sampling imports. One interesting thing here is that actually, I mean, the automatic system only counts the fish that is in the top, so don't count all the fish. But also in the ports, they don't count all the fish. They just take 1,000, for example. And from that, they extrapolate, like, what are the proportions of each species. If both systems are good and both systems are statistically robust, they will get similar results. If there are discrepancies, there maybe is a bias in the sampling in the port, which I don't think so, because their methodology is quite established, or the machine learning methods have some limitations. In this case, we see that there was a lot of overlap in fish and the size was underestimated. And in this case, well, we could say, well, the sampling import can tell us about this. But for example, the sampling import, if there is rare species, only taking 1,000 individuals probably will not be very good at identifying that. And with the automatic system, maybe you can sample 10,000 or 100,000. Still, they are complementary. How we know that artificial intelligence is doing well? Because we have some way of verifying that. And we have also to train the models. So we are still, I don't think artificial intelligence systems will replace humans. They will allow us to do, instead of 1, 10, 100, 1,000. That is my opinion. Another example was this work. We was looking at mapping fishing activity. We was comparing satellite data from EAS. EAS is a system that the vessels have not to collide between them, and that broadcast can be taken by satellite. And we have also, for example, in the case of fishing vessels, we have BMS, that is a system installed in the vessels that they are monitored by authorities and enforced. So we could compare whether the EAS data was good in comparison with the BMS data, and identify which fishing years the EAS data was good and which ones not. But there was regions of the world where we don't have BMS data. I mean, Europe is quite established, but we was doing atlas looking at whether we can map the fishing activity in all the world. So what we did is compare with catch data. We know the catch data can be a proxy of fishing effort, but is not. You cannot estimate fishing effort from catch data. But looking at the discrepancies between EIS and catches, we could say, oh, wait, there is reported catches here, but there is no EIS activity. Probably something is missing in the EIS activity. Or the opposite. I mean, we can see the EIS activity, or is misclassified as fishing activity when is transport, or maybe some countries are not reporting their catches correctly. So looking at these discrepancies, we can identify limitations in our systems or limitations in the data. So it's important not only to have robust statistical variation, but try to find these sources of ground truth, independent data that can tell us whether or we are seeing everything or not. And to end, I want us to show some of the other projects we are working on. We are working, for example, on mapping benthic biodiversity with image analysis. We are working on mapping human activities from satellite data, like aquaculture, wind farms, and vessels. And we are working also with this, what I show already, fishing, improving the classification of fish in fishing and combination with genetics, and also working more on how we can use more artificial intelligence and big data for mapping or even identifying illegal fishing activities. And I hope I didn't go over time, Miguel.
Oh, thank you very much, Josean. I think it was great. Thanks a lot for this presentation that went from testing to see if your data sets are really robust to apply these methods and all these practical examples. So thank you very much, Josean. I now ask Mihailo to go ahead with this presentation.
Yeah, sorry, just trying to get the screen shared.
It's okay.
Cool, can you
It's
see
working.
that?
Yes, all good. Thanks a lot, Mihailo.
Let me move that down here. Okay, hi everyone. I'm Mihailo, and today I'll be really just talking about the coherent mapping study that we've been doing at Obama Next. And while my name is on this, there's a whole bunch of other people that are involved in this project, quite a number. But I'll be mainly focusing on the coherent mapping studying framework that we were developing and my work specifically in this. So without further ado, we know that coastal ecosystems have experienced serious declines in water quality over the past couple of decades, with a lot of associated losses in important benthic habitats and species. To mitigate these, we have a lot of new policies that have been established to reduce the underlying pressures, but there's also been a lot of monitoring programs that have been developed to kind of support the evaluation and of the efficacy of these different policies. Unfortunately, traditional survey methods have been quite limited in terms of spatial coverage, and they're also predominantly quite expensive. So satellite remote sensing and more recently drones have been kind of sought as the cost-effective method for mapping, especially because of their high spatial coverage and their high availability. Performance-wise, they've done quite well, but more often than not, there isn't really a standardized approach to the data gathering, validation, or even the model training, which makes reusing these models or even the data they're trained on quite difficult for future endeavors, which is what kind of gave birth to the CMS study, which we conducted in summer 2024 with a focus on eelgrass and macroalgae. So the objectives of the CMS and what it actually is a kind of framework development exercise to investigate a standardized approach to the whole mapping pipeline. We were looking at investigating modern mapping methods, namely convolutional neural networks. And I say modern in quotations because there are more state-of-the-art models at the moment, like transformers, which are not really fit for the amount of data that we currently have. And we wanted to also examine the use of a unified mapping model, which is an ongoing process right now. Lastly, we wanted to integrate high-resolution drone observations with satellite remote sensing for upscaling benthic mapping, which is also ongoing work. And today's talk will be focusing mainly on the framework and the drone aspects, with a little bit of a sneak peek on the upscaling results. Because that's, if we had more time, maybe there's a second webinar, we can cover the upscaling aspect as well. So, okay. So the CMS framework builds on work done by KVLL in 2024, where they attempted to kind of standardize the data gathering and annotation approach. Here we take it one step further and kind of standardize the entire workflow, or at least provide some prescriptive guidelines for that workflow. And these aspects of the workflow can be separated in mission planning, field operation, and post-processing. Each of which, if you have no documentation or there's no sort of standardization, can make it very troublesome later down the track. And of course, you can see these are kind of the standard aspects of mission planning, like what drones you're going to use, or what satellites you're going to use, where you're going to do it. But the underlying theme there is also the documentation aspect for data set creation and creating models. So why develop such a framework? Artificial intelligent models like convolutional networks and transformers are very, very powerful approximators, and that's a good thing. It means they can fit well to the underlying data. The downside is they can fit maybe too well. And if you work in a complex domain like the marine domain, when you have a lot of photometric variation like sun glints, shadows, and light scattering, you can get easily overfitting results. As it currently stands, drone-based models tend to also be locally developed. That is, they're created for specific water bodies, or maybe a couple of water bodies, and their transferability between different water bodies is quite poor. So as an example, I cannot get a Norwegian trained model to work on Danish waters, and to adapt that model for my waters will still involve a large amount of data collection and data annotation. But a part of this goal is to actually create a data set that has all the underlying documentation and feature building so that we can actually do that kind of mapping quickly and make it more transferable. So more data in the end will lead to better generalization, but only if we do it in the right way. So here is those three aspects of the workflow that we've broken down into kind of what's really important about maintaining standardization, at least documentation on that, because each of those aspects govern a very important part of the processing chain, which affects the performance of the final map created as well as the model. And if you don't document any of the decision made in these aspects, you can often hide underlying issues. And the differences between these particular aspects are something we call domain gaps. That means you create a difference in kind of the data distribution that you train your model on and the data distribution that you apply your model on, which are your target domains. And so an example of that is different senses from environmental conditions during your acquisition phase, but also all the way down to how you interpret your annotations when you create those maps or the training samples for those maps. So for this, I'll cover some key aspects of the acquisition, the context, and post-processing. It's not exhaustive of what is in the actual framework itself and the operating procedure, but we will be publishing the full framework and operating procedure on GitHub in the coming months. So to kind of contextualize the work we did in the summer of 2024 and a little bit in 2025, this is the site selection aspect of the beginning of the framework. Here we're choosing. It's kind of about standardizing the way you choose the site. Because we're working with eelgrass and macroalgae, we're looking at shallow remote sensing. In that case, we were looking up to a depth visibility of 1.5 times the second depth. We wanted to, and I guess in a more general sense, choose areas of interest that were large enough, 5 hectares. So 5 hectares gives you enough room to create replicates for annotation and testing your models on, but also large enough to be associated with upscaling for Sentinel satellite data like Sentinel-2 data. When you choose these areas of interest, you should pay attention to the habitat composition. In real life, you're going to get a mixture of homogeneous and not homogeneous or heterogeneous biotic and abiotic habitats. But you want to include a variety of sizes from small to also very large enough that a Sentinel-2 pixel can cover most of it. And lastly, because we are looking at monitoring frameworks, we wanted the areas of interest to be underneath an existing vegetation mapping region across all. So for mission planning, we investigated two main aspects. Here are the drones and the Sentinel and the satellite data. For drones, we looked at the DJI Mavic 3M, which is an off-the-shelf drone providing some multispectral capabilities through water sensing, as well as RGB with high resolution. But more importantly, in terms of a framework for mapping, it has an RTK GNSS module, which allows for high 1 centimeter resolution georeferencing of orthomosaics or any of the images that you collect. And this is important if you want to investigate upscaling with satellite images like we did, but also for annotation, making sure what you annotated is also the right place. And of course, for satellite data, we look at Sentinel-2 because of its freeness and good resolution, I guess. So here we have just a couple of examples of the pixel differences, especially when it comes to heterogeneous habitats, which then are lost in a 10-meter pixel. I guess more importantly here is also during the operations that we did on the ground during the day. We're looking about ground truthing specifically. So we need to know what the drone is seeing and find out to actually establish a way to kind of standardize how we approach that. So in our case here, we use GNSS RTK sticks. I'm not sure what the technical term is for them, but they have high positioning accuracy. And we use that alongside, and I cannot stress enough, importantly, taking images and video examples of the patches that we're choosing for annotation. Images and video examples are quite important, especially because it covers the kind of subjective variability that you might expect when you're trying to annotate the orthomosaics or the images later. And that leads into something very important because your overall model performance and reusability of these data sets for future models or future studies is highly dependent on that ground truth data that you choose to use. And by having sufficient, or in this case, a lot of images and videos of these annotation regions, you can have at least a way to revisit the interpretability of your ground truth data. And you can see here, if we would look at some of the drone data from Charlottenlund in Denmark, we can see there's a mixture of, I'm not sure if you can see, here you can see my mouse on this thing, quadriphyllum with eelgrass, heterogeneous habitat here. Here is a kind of seagrass and sand, but seagrass dominated habitat. And here is another seagrass and quadriphyllum habitat with seagrass dominating. But because we have these images from these locations, we can say confidently that this particular region here is eelgrass dominated. And we can kind of revisit that at a later track for interpretability. Other aspects of field operation that we try to standardized is actually when to go out. If you live in Denmark, the weather can change within a couple of hours, and even between days, it can be quite stark difference. So we try to target days of even illumination during clear skies or enough lighting during overcasts, and especially for low wind speeds. So you can see here the two images here. On the left, we can see a part of Froskel Fjord. And while we were imaging during the morning, a fog rolled in, and of course that ruined a lot of the data that we gathered. We revisit the same location the next day, and we had slightly stronger winds than normal, and as well as a biofilm forming on the surface. So by targeting these ideal or close to ideal field operating procedures and then documenting them, we can at least create a data set that can be reused later on. Maybe you want to explore some more robust machine learning models that deal with these variations. Here's just an overview of the processing pipeline that we use for standardization. We took our learning site data on the left here and fed it through an AutoMosaic pipeline hosted by CB in Norway, and they created mosaic outputs. But because we use RTK modules on our drones, we can have strong georeference and alignment with the Sentinel-2 images, which are then also corrected by our partners in RBINs. And this is what the annotations were done on the mosaics, and then we did our mapping algorithms. But the key point here is that it doesn't matter what kind of software you use to create AutoMosaics or what kind of algorithms you use to do the correction, but you should actually document it so that we know that this particular Sentinel-2 image that you have been used has been corrected by RBIN's pipeline, which uses X, Y, and Z algorithms. Or your AutoMosaic pipeline is done by Agisoft Metashape instead of WebODM or something like that. And then, of course, documenting the resolution. Here we follow Kevil et al.'s annotation procedure, which is a hierarchical classification system where we had level 1, level 2, and level 3 classifications. The higher the level, the more granular the description. And in this case, you can see, for example, algae at the coarsest description, brown algae at the second level of granularity, and then Fucus serratus, for example, at the species-specific level. What this means is that you can, in the future, when you're doing the annotation, you allow the annotators who are maybe specialists who then use the ground truth videos and then interpret the AutoMosaic pixels themselves, allow them to kind of annotate up to a level of confidence. And it could be at any of those particular levels, but also can include not annotating anything, which is this gray area here. So if they're not confident annotating whatever this is, they just don't annotate it. The AutoMosaic then for our models would then chopped out to 448 by 448 pixel slices, which would then fed to a UNet model. I'm not going to spend too much time on here, but just for completion's sake, we did use a UNet that used a ResNet backbone, and we did weighted cross entropy, as well as a combination of weighted cross entropy and dice losses, so that we can balance out the class imbalance as well as the fact of using partial annotations. And this is kind of the training scheme that we employed. Some warm-up epochs, early stopping, and equating during loss. So kind of standard. So in the end, we collected drone imagery from 6 learning sites. Here, just an example of where the sites are. I worked mainly in Denmark, and my partners in Norway did mostly up here on the northern coast, but we also had the Balearic Sea and parts of Bulgaria and Romania. These are kind of the resulting AutoMosaics that were created. The largest coverage we had was in Norway at 178 hectares, but we also had large coverage in Bulgaria at 150 hectares. But we targeted a minimum resolution of 5 centimeters for the RGB, and as well as the MSI. But in some cases, depending on which type of drone was used, we also had MSI up to 9.4 centimeters for multispectral imaging. And that's from our partners in Norway. Model performance-wise, we used your standard confusion matrices to interpret the data. If you're familiar with them, you can kind of see what the true playable classes are over here, and then what the model interpreted it as here. For example, gravel in this particular location in Norway was misinterpreted as bedrock quite often. But overall, we saw strong performance across the data sets when we created local models from them. That's this here. With an overall performance of balanced accuracy of 0.78 and a weighted F1 score of 0.87. And our key, I guess, benthic habitats is algae and angiosperms at the lowest granularity achieved 0.8 and 0.7 respectively. And we have some examples here from Norway and the Balearic Islands. Now here's just an example of how we can explore classification at different granularities. So these are the classifications at L1, which is the coarsest granularity, all the way down to species specific. As you can see, the more species specific, the more evident class imbalance is present, and which makes the classifications a bit more uncertain. But also does provide a little bit more granularity in terms of what is actually lost. For example, we maintain a lot of deep water classification at the lowest granularity, but we kind of lose that a bit as we go more or less specific, I should say. Again, this is just early analysis. We will provide a full analysis. I'm going to have a paper soon, so we can have a full analysis. Hopefully, can post it up here to read. So here's just a zooming in of that particular location. I apologize if I'm looking to the right because I have the screen on the right side here. But you can see at level 1, we do kind of overpredict on algae. But as we go down to level 3 specificity here, we are kind of overestimating where eelgrass is actually present. And that's these sections here are actually eelgrass. But a good thing about this is that we can peel apart these models to look at some of the uncertainty here. And as expected, we find a lot of uncertainty around any of the class boundaries. So here, the values are p-values from 1 to 0. Anything below 0.5 is not great, and anything closer to 1 is great. But as you can see in A and B, anywhere near the class boundaries, the model is definitely more uncertain, which is good because it's expected. But then we see here, due to class imbalance, we can have sometimes something is like cursor vegetation being quite uncertain. We can then explore uncertainty under those different classifications. As you can see, as we get to more specific, class imbalance rears its head, and it cannot be overcome without getting more data, but we get less certainty in some of these pixels. And this is important if you're trying to create an upscaling process as well, because that means you can choose pixels in regions that have higher certainty. Lastly, we want to investigate some cross-site performance. So I mentioned earlier that transferability between sites is not that great and performance is poor, and that is true for most cases because of how strongly these models fit. Here's an example of that that kind of loss in model performance. Here we have Norway predicting on a region in Finland for the same benthic classes, and we can see that there is quite a bit of overprediction on algae, which is this orange aspect here, and we kind of mistake a lot of sediment for eelgrass. With that being said, this is ongoing analysis that we look to try and improve this kind of cross-site performance, unifying all the data that we have to try and hit a, I guess, unified EU model. A tricky aspect with not that much data, but kind of underpins the need for actually creating these data sets in a standardized way, so we can actually build more flexible and more robust machine learning models. So lastly, as a promise, some of the upscaling data. Here we are looking at Sentinel-2 RGB image of one of our Norway sites. We used our annotations to train a Sentinel-2 based model, which you can see here in the middle. And in the last model here, we integrate drone observations with Sentinel-2 observations to try and improve the granularity of the classification. And we can see we are quite successful in turning what misclassifications as sediment from these large pixels into closer approximations of rock or bedrock. There's some clever machine learning undergoing underneath there, and this is done by my colleague Gladys Villegas. So hopefully that can appear in a future mod webinar. And just another peek at what some of the results that she had, we found that by actually moving towards integrating drone classification and imagery with Sentinel-2 based observations, we can actually get more stable performance. And these are across 4 sites, 3 of which are in Norway and 1 in the Balearic Islands. The left is based purely on the annotations, so 300 to 400 annotations for each of the sites versus improved drone-based observations. And you can see a more stable performance, especially in the F1 scores. So I guess in summary, we tested this framework across 6 learning sets in the EU, building upon work done by Gavil et al. We'll be updating the standard operating procedure in the framework based on feedback from all our participants in the OBAMA-NEXT consortium. We developed a convolutional neural network that does grid mapping and investigated its performance across different taxonomic resolutions during the classification, as well as some of its cross-site performance. Future work, which is hopefully happening, which is going to be completed very soon, is actually look at improving cross-site applicability and looking at developing a unified model. Thank you.
Thank you very much, Mihailo. Great work, and it highlights a lot of partners that put a lot of effort in the past few years in the Solomon X project. Thank you very much. So for those who have questions, feel free to write in the chat or just click on the icon to raise your hand. While you're thinking, which questions you'd like to ask, I have a few that I've been thinking about, and I'll start, Mihailo, with a question to you. So you mentioned this let's say cross-site limitations that are being improved and tested. So would you say that the method as it is now would be more suitable for monitoring the same sites over time, or do you think that developments in AI tools and models will allow that cross-site comparison can be more easily done without a lot of field work?
So I mean I think the cross-site performance is predominant because we don't have enough data, and you cannot find data sets online or even through partners that are kind of unified in a way to build a more robust model in that aspect, because we have no idea how they've interpreted the ground truth annotations or even the heights of the resolutions of the image. So this kind of framework is about setting some sort of standard that we can follow, that we can actually do this kind of data set sharing. So I don't have to rely on getting more data in Denmark. I can maybe borrow additional data from Finland or Norway or maybe Sweden, and integrating that and then I can pick and choose which data sets to add. So this is really about creating that kind of data set, so that in the future we can actually do maybe a Northern Europe-based model, and then maybe a Spanish model or something like that. But yeah, the biggest hurdle is data set availability and numbers.
Yeah, that's let's say an issue that Josean covers very much. The importance of having a good data set and test the robustness of the data set and different methods to make sure that they are robust and reliable. Josean, how do you deal with the data set that it's not that large that you can partition it and still be robust? You just drop it and move to another data set and research question, or are there new methods that can still be to be used when your data set is not that large or that robust?
Well, there is methodologies you can use when your data set is small. I mean, and it's even more important to have these data partitions, because at the end you can that way assess what are the limitations of that small data set. Actually, during my PhD thesis, I was forecasting anchovy recruitment, the new anchovy that could be fished, and we have only 34 observations, and still we was able to do something. But what we was not forecasting the number of the recruitment. We was just saying what was the chances of having low, medium, and high. So at the end, if you have few data, you have to adapt to that. But still, that worked well. Actually, it was even used like one more evidence to open the fisheries when the anchovy was recovering, and it was an early assessment before there was any other data. Then there was more detailed survey data where they was going with vessels to take larvae and eggs and so on. And actually, the system was working quite well, because even it was a very basic estimate. It will say only if it was going to be a bad or a good year, not saying anything else. Still, because it could do it very early, was very useful. So at the end, there is methods and things you can do to adapt, and you have to be also realistic what you can achieve with what you have, and sometimes something is better than nothing, and we have to be realistic. And also about what was being said before, when we was doing aquaculture mapping, it was funny because we have some in one region we have like the official sites, and then our system was doing wrong when we compare with the official sites. But then we was looking visually, and the official data was wrong. Actually, our system was doing well, and the official statistics was outdated or something. So sometimes you find these kind of things.
I guess the tools that are available allow us to test how robust is the data set, but they might not be able to and there's to assess if the data set has errors and inherent biases that you cannot overcome them, I guess, especially in historic data sets, maybe.
I always like to speak with experts to see what you see makes sense, and then they can suggest, oh, I see something weird here, or when we was doing this thing of for example, the comparison between fishing activity from BMS or the EIS, the first thing I did is to produce maps and show to the fishing experts. And for example, we realized that there was an error when some authorities sent us the data. They forgot to send the data of one fleet. And we could only identify that, well, because I asked experts, do you think this makes sense? And say, oh, this weird, I think there's something missing here. And then, so yeah, I mean, you need to find many ways of looking at your data and your outputs, and the experts are really, I mean, they can be also biased sometimes by what they know, but I mean, you need to also that long-term expertise to contrast what data you have and what is the output of your. But this applies to any modeling, not to artificial intelligence, actually.
Indeed. Thank you, Jose. Mihailo, if I may, you mentioned that there's this a whole new work on the upscaling component, and probably that would need 1 hour of a presentation to fully explain what's being done. But can you tell us in a brief summary of how is the process to upscale from your local models that are working well locally, but to make sure that they work regionally? It's you mentioned, of course, there's satellite data, but it does not have enough granularity, and then you need drone data or other field work. How is the process to upscale these models to larger locations or even regions?
So the upscaling with Sentinel or with satellite data really hinges on the fact that the satellite is a kind of a constant observer, it's one or two sensors that are looking at each of these regions. So it reduces any of the variation that you would expect from using different drones across different waters. So there's some level of homogenization in the acquisition aspect of that. And so by leveraging some of the high resolution but low altitude data that we get from the drones, and particularly the classifications that we output from them, we can actually create better training samples for those heterogeneous pixels that we see from the satellite. So the integration between drones and Sentinel pixels is really about kind of improving what kind of data we can actually use to train those satellites. As opposed, so if we go to, that's the upscaling with satellite section. If you were to extend drone coverage to different coastal regions, it really is a numbers game in terms of having available training data. And the standard operating procedure allows us to actually just kind of get information on what data we actually have created for our data set, and then choose the right ones that can be work for our region and the classes that we want to cover. Because as I said, right now there isn't a kind of existing data set that can do that really nicely. And so these are kind of like first steps into that.
Nice. Thank you, Mihailo. We have a question from Vasil.
Hi, I'm sorry I joined late and maybe I missed something. So please excuse me if the questions are not to that extent relevant. But in diversity, where I'm working, we have a problem with the data. In order to demonstrate good results, analysis which is valuable, you need to have good data. And one of the problems we face is that we don't have sufficient data. We don't have enough good data in order to demonstrate what we can do with it. So from this point of view, I think that in our projects, it's also valuable to pay attention to the metadata and the experience which you gather when you are successfully analyzing certain data. So my question is related to the management of the metadata and the knowledge used to process the data. Do you, for example, produce ontology of the data analytics, because you demonstrate certain successful analysis of or using certain good data. But in order to be transferable, this experience needs somehow to be recorded and put in a format which can be reused. So that's why I'm interested in the problem of maintaining metadata and ontology of the data processing itself.
Thank you, Vasil. I don't think we covered a lot of the topics of metadata, but I don't know, Josean or Mihailo, do you have some inputs to provide?
I mean, I could go. I think this is quite relevant to kind of the coherent mapping study. So while I didn't show it directly, we do have forms that people fill about where they've collected data, what they've collected, as well as the locations and descriptions of on-the-day collection. So some example of metadata is, for example, sticky disk readings as a way of measuring the true water visibility, something that you might not get in a drone data set. And to do this per location on the day is recorded in the metadata format. I would say the process is not fully thought out just yet, but again, it's just early steps into that kind of process. But this metadata, I think, is what helps build the data set. And being backed by some ground truth imaging, we can control a lot of that kind of interpretation so that we can always get good data, or we can filter out maybe something that's not as good later on. Because right now we have no way of gauging that.
Thank you, Mihailo. Josean, do you have any comments?
Well, I didn't cover in my talk, but I mean, there's more and more efforts to related with fair data and other principles to try to standardize things and make easier to share data and that is well documented. And there is more and more tools that helps you to check your data, but probably something that still there's a lot to be done. And even if we advance with that, I always like to speak with the original generators of the data or the people, because I mean, we can automatize more things, that data is more easily available and to do fast checks. But at the end, I think one important thing is also that the data can be traced to the original people that produce and worked with it. And that is also that we have also to work on not to forget that at the end, the people that is my opinion. Not very computer science thing, probably.
So just before we wrap up, I have a tricky question for you. You know, if I don't know if we have early career researchers attending, but if you're talking to someone who's studying a master's or a PhD in this topic, this field is evolving super fast. Are there any recommendations that you would give for someone who's starting to work on these tools for biodiversity monitoring, or any pitfalls that they should try to avoid? What would be your recommendations for someone starting on this?
Well, my recommendation will be that you have a team that can support you well from the computer science part to ensure that you understand what you are applying and the right way of doing it, and that you are also covered by experts on the field. Like if you are doing something about habitat mapping, try to speak with people that know about habitats, about remote sensing, and have also people from computer science that tells you which kind of models you can use and explain you why and how validate things right. So I think that will be my advice, and that they speak with a lot of people to make sure they learn all the sides of the things.
Thank you. Mihailo, any tips?
I mean, I concur with Josean. I think my entire academic career has been working closely with marine scientists, because kind of managing expectations and interpretation from my side with what they want is quite tricky. And I've had a lot of miscommunication and learned to overcome that aspect. But apart from having a good team, I think one of the important things is to be careful about model interpretability. We like to think machine learning models and AI models produce really good results, but model interpretability and the kind of contextualizing your performance is important. And I find that often is somewhat overlooked, especially if you were to just apply models out of the box. I think, yeah, it needs careful consideration. Again, that kind of goes back to actually talking to experts, whether that's computer science experts or marine science experts.
Perfect. Thank you very much. So there's a question in the chat. Could you provide some critical issues or points related with the quality and sufficiency of ground truth data? And quantity means, frequency per unit area. I guess this is more for Mihailo.
I think it depends on what part of remote sensing you're using. For example, if you're using Sentinel-2, you need large amounts of data to cover, at least spatially, to cover Sentinel-2 pixels, because otherwise you'll get heterogeneous pixels. And it's something that we try to overcome by integrating drone-based observations with the Sentinel-2 observations. With that being said, for actual drone-based work, ground truthing quantity per unit area, I would need to go back and calculate what ours was, but essentially when we targeted 5 hectares, what we really wanted to do was collect at least 1.5 hectares replicates within those regions that we can use to annotate and validate our data. So I guess as terms of quantity, try and maintain it as equal as possible between the classes, but have sufficient. I don't have a specific number there, but yeah, critical issue would be class imbalance and actually having good number of replicates within your area of interest. So just have large enough area that you can do that in. I'm sorry I don't have a number specifically on that. I'll get back to you eventually, because then I could actually calculate it. I could actually calculate it per class, but I don't have that on me right now.
Okay, thank you, Mihailo. We need to wrap up. So I'd like to thank again Josean and Mihailo for being available to share this fantastic work. I would like to thank again all the audience that participated in this webinar. I forgot to say in the beginning that this MOD Alliance it's an effort from let's say the 3 persons here in the call: Teresa Fonseca from LPN representing Diverseas, and Matilde Vidal from Area in Innovation representing Marco Bolo, and myself, Miguel Leal from Science Crunchers representing Obama Next, all working on the communication dissemination component. The next webinar will be exactly in 2 months from now, so May 5th. The topic will be From Coasts to Microbes, Participatory Observations with Diversity and Selling for Science. And the presenter will be Luisa Gunzel, who will be opening the registrations soon. So once again, thank you again for participating. I hope you enjoyed, and have a great rest of the day. Bye-bye.
Thank you, Miguel. I forgot to say that some of the nice figures from my presentation are from Science Crunchers.
Thank you.